So, Professor Bergin, thank you for being with us today. Thank you for being with us, and we look forward to talking to you.
Yeah. And so we mentioned that I think it was last weekend that you went to go see the Lucy mission in Florida. So
Yeah.
I guess we were wondering, like, how was that? What exactly went on, and like, what exactly was the Lucy mission about?
Right. So this is NASA's Lucy mission, which I'm not involved in, but I'm good friends with the principal investigator, Hal Levison, and Hal graciously got me on the list to go down to the launch. And so thank you, Hal. So I went to Kennedy Space Center, and the day before you have to go get your launch pass.
That's cool.
So you go through the gates and of the visitor center, basically. And you don't need a ticket because the pass actually has like 48 hours, which is kind of nice for you to wander around. And what I didn't fully appreciate was the number of people that were on the extended list for invitations to the launch. And so there was this massive line there to get the pass, but that's okay. All right, so 80 degrees, wait in the sun. And so then I got my pass and got to go to see the rocket that took astronauts to the moon, right? So this massive, huge, the Apollo rocket and the Saturn V. It was just insane, and the shuttle Atlantis, and so it was just spectacular, The launch itself, it was at the launch window opens at 5:34 a.m. and they want to launch right on time, right when the window opens. It was about an hour and something window, and I'll talk about what Lucy is in a minute. But you allow for things to happen, right? So that can always happen. Things can be delayed, and so I got up at the buses start running from you go to the visitor center, and the buses start running. They were running, I think they said from 2:30 or no, what was it? Yeah, it was 2:30 to 4 a.m. and they took us to another site on there's an inland waterway there, and so the rockets launch off on an island, and not an island, right? A peninsula or something, and you're across the water from it. And so I got up at 2 a.m. To drive to the Space Center, and there were just people everywhere. Oh my God! Just because there was a space camp or something and just lines of different things. And so then you wait in line for a bus, and you go to this place, and you sit on bleachers. I got there 3 a.m. So I sat there for like 2.5 hours. Had people wandering, trying to find the best spot so they could see this thing. But then it was when it launched, it was just spectacular. The clouds, there were clouds, and I was worried about that. But the rocket then went through the clouds, and as it came out of the clouds, the light the rocket was created reflected off of the top of the clouds and then illuminated the clouds that were above the rocket. It was amazing. The video is on YouTube now, the one that I took, which you can find by Googling. I think it's Lucy Launch and my last name. We'll get you to it. It's spectacular. Lucy itself is a mission to go to Jupiter's Trojan asteroid. So there are stable points on the orbits of all the planets between the interactions of the planet and the sun. And basically anything that gets stuck in an orbit that is sort of almost trailing and in front of Jupiter is stuck there for forever. And these Trojans are believed to have been implanted very early in the history of the solar system, and they may bear a record of the interactions that the planets were doing with each other at that time. And so there are true fossils of the history of the solar system that are going to be probed by Lucy.
So is this something that's closely related to your work in solar system formation? Do you have any scientific interest in the results of this mission?
100%.
Aside from just curiosity?
Yeah, I'm super excited. It's so cool. They're going to try and trace where these things came from, and they could have come from pretty far away. They could have been coming from, much greater distances than where Jupiter is right now. And they're going to look at what they call the colors and what the composition of the surface is to try and track and see if these things are similar to asteroids or comets or maybe some mixture of the two. And so what I do is I want to understand how the Earth came to be. And so the history of the solar system and where the giant planets were and when. It's possible that Jupiter formed at greater distances and migrated in, and there's models where Jupiter and Saturn went in and out, and all those motions and that dynamics has great influence on how terrestrial worlds are constructed. And so any information you can glean on that is just gold. It's just pure gold.
So a not so shrewd observer would very quickly notice that the inner planets in the solar system are rocky and the outer planets are gaseous. Is there anything profound about that, or is that an accident, or just a feature of our solar system that is not sort of a general feature of other solar systems?
So there is a question as to why that would be, right? And the solar system suggests to you that giant planets do not form close to the star.
Right.
So why would that be? There are Jupiters that we observe in other solar systems. About less than 10% of the systems have Jupiters parked right next to the star, so-called hot Jupiters. Those are believed to have migrated in, but there are individuals who've written papers arguing that perhaps they could have formed in place. So under those theories, that would lead you to say that that it's possible, and maybe there's nothing profound about it. But my guess is, and this is just my opinion, is that it's easier to make bigger planets further away. There's a model, I think a very persuasive model out there about how planets are born. The current idea of making a terrestrial world, an Earth-like world, or a Jovian world. So Jovian world first, you make a sort of like a 10 Earth mass core first of solids, kind of like the rocks that we're sitting on right now, or the big rock. And then that gravitationally captures gas from the surrounding nebula. The current neat model of planet formation, instead of a bunch of big things getting together to construct an Earth or that Jovian core, is that you accrete pebbles, sort of centimeter-sized rocks, and it's a lot easier to build up mass from smaller things than it is by grabbing a bunch of 100-kilometer-sized rocks. And there's a good idea that the pebbles might be larger, or allowed to be slightly larger in growth in the outer parts of the solar system. And even though you're creating these tiny little pebbles, when they're a little bit bigger, there's more bang for the buck, and you can make bigger things. And so that's one idea out there that is persuasive to me, but the devil's in the details.
Yeah.
Always.
And then in your own research, are you looking at the structure of our own solar system and observations and probes within our own solar system? Or, for example, within like the past decade or two, we've been able to look outside of our own solar system at like planetary disks and other solar systems? So how do you kind of balance your research?
Yeah,
or is it
Sure.
It strikes me that the solar system is an extremely convenient place to start looking because it's close and we can see everything well. And I assume it would be very tempting to generalize the solar system to other systems out there. And how closely linked, how typical is our solar system in that sense?
Sorry, so that's one can go very big in that question. So let's say this, right? We're on the only inhabited planet that we know of right now.
Right.
So in astronomy, we talk about habitable world that could possibly harbor life. We're inhabited. And we have the best data that we're ever going to get from this planet down to minute details. And the same goes for the asteroids and comets. They provide us with minute details. And I think those minute details can be useful even for an astronomer such as myself, which is why I try to pay attention to them. And so then, astronomically, in terms of remote sensing, we can't, if I want to look at the formation materials, we can observe disks. And it's a lot easier to detect things that are further away from the star than they are closer to the star. So it's very hard to look at the region where terrestrial planets are being born. So part of my science is to look at these disks and understand what is the composition of the gas and the solids out where Jovian worlds are being born, and what does that tell us about the formation of Jovian worlds. So that's one statement. The other thing is that stuff move around. They don't necessarily stay in place. These pebbles, when they're born, millimeter, centimeter size pebbles, they're born in the disk. They grow to larger sizes from smaller materials seeded to them by the general interstellar medium when the collapse to the disk occurs from a centrally concentrated object. Those pebbles can move, and they can move inwards. They drift inwards. And so by studying the outer disk, you may be inferring what's going on in the inner disk. Inner disk is where terrestrial worlds are being born. But then there's other ways to do it. The James Webb Space Telescope, when it launches, will be observing lines from emission from molecules that have their excitation conditions such that they will only emit from the inner part of the disk where the terrestrial worlds are being born. So you'll be able to approach and try to understand and characterize the composition of the disk, both in the giant planet-forming zone and the terrestrial planet-forming zone, by combining the stuff that I could do now with the Atacama Large Millimeter Array, which is probing sort of like, from 3 Earth-Sun distances out, and the James Webb, which will be, the 3 Earth-Sun distances in. And then you understand the composition from astronomy, and I look at the composition from the planet that we know about, the Earth and all the other planets, and try to understand what does that tell me about how likely it is that you're going to make other Earths. And so that's sort of the big picture. There's lots of really interesting facets within there.
Something that's always puzzled me is, how do we know what the Earth is made of? Because, from my understanding, we've only drilled sort of 10-ish kilometers down into the Earth. And the models of the general Earth structure seem fairly detailed, and, they tell us that there's such and such materials here and here and in such and such proportions. How do we know that is the case? What evidence do we have that what led to the creation of those models?
Okay, so here's where you push me out of my comfort zone. So I work with geophysicists and geochemists, including one geophysicist here, Jackie Lee, and another one, Mark Hirschman at University of Minnesota, that do that work for me.
Okay.
And so I provide the astronomical context, and we work together in interdisciplinary fashion, along with Fred Chesla, a planetary scientist at Colorado, and Jeff Blake, another astrochemist. He's at Caltech. And our interdisciplinary team tries to put all those things together. And so what you can do to try to understand the Earth's structure is to look at volcanic outgassing,
okay,
and various other ways where you can access the deep mantle. And then you take the things that you know about, so there's some elements that they understand what's going on, and then you extrapolate from them as to what the unknown elements would be. The hardest thing to get at is the Earth's core. Okay, so we know the Earth's core is iron and nickel dominated, but it's clear that there's a light element present in the Earth's core. And that's because the density that's measured from the Earth's core, which you can get from seismic waves, is a little bit offset than what you would expect for iron at the temperature and density of temperature and pressure expected for the Earth's core. And so there's some light element in the core, and so there could be a lot of, if carbon, for example, were that light element, there would be more carbon in the core by a lot that would dwarf all the carbon that's on the surface and in the upper mantle of the planet. But it doesn't have to be carbon. It could be anything from hydrogen to silicon. So there are knowns, but there are some things that people can figure out.
Okay. And we also noticed on your website for your research that you are also interested in the kind of the lack of carbon or the lack of nitrogen on Earth and
Right.
maybe other systems.
Sure.
And so I was wondering if you could talk a bit more about that issue.
Sure. Yeah. If you look at the Earth, and even trying to account for what is in the core, so our team tried to figure out how much carbon you could stuff into the core and be consistent with all the constraints. And there is a limit. And so the Earth is a carbon poor body. And what do I mean by that? Is that if you take the carbon that was available, that is the cosmic abundance of carbon. Now, in interstellar space, half of that carbon is in refractory solids, that is tiny little submicron side rocks, basically, carbonaceous rocks, but they're super tiny. And all of the silicon is in that material as well. And that's those two flavors of rocks, carbon and silicates, provide the seed material out of which terrestrial worlds are made. But if you look at the abundance, okay, so carbon is more abundant than silicon. And so if the Earth was made of a mixture of the solids that are out there, we should be a carbon rock, about a factor of 5 to 1 in terms of elemental abundance relative to silicon. But we're not. The Earth is carbon depleted by many orders of magnitude with respect to that. And so what that means is that we received less carbon than was available at formation. And so what sets that up? And the same thing goes for nitrogen. We're even more depleted in nitrogen. And you think of the Earth is a water world, right? But we're only like 0.1% water by mass, and that's just a generous accounting of how much water could be stuffed in the deep mantle. We are a water poor world, we are a carbon poor world, we are a nitrogen poor world by orders of magnitude compared to what was available. But yet we, as in life, is here. So what does that mean? Does it mean that this is what's required to make life? Or could it be, if you receive significantly more of that cosmically available carbon, that you could have life be present? And of course, we don't know the answer to any of that. And so the question is, how can we explore that? And so that's where we are now. We're trying to understand what kind of expectation values might you'd expect for when you form an Earth. Would you get more or less? And it's very complicated. If you provide carbon when the Earth is young, the Earth started molten, right? So they had a magma ocean because of all the accretion, and that's why we have the iron-rich core, right? All the heavy stuff sank to the center, and if carbon was present with that iron, it would be carried down to the core and not be present on the surface. And so it's very complicated. You have to account for the gain and loss terms of carbon throughout all the various stages of planet formation, and that's what we've been trying to do so that we can put it together and make some predictions so that we can try to understand when all these amazing exoplanet atmospheric composition measurements that we hope James Webb Space Telescope will do and all the ground-based telescopes are doing, when we start to get a better idea of the landscape of what planetary atmospheres look like, maybe our work can feed into that and we can understand a little bit more about, what all this means for carbon supply and life.
How do we look at that planetary atmospheres that are not our own? Because it seems to me like when you're looking at a star or an object, it's you usually see you see a sort of a 2D disk, and the atmosphere should only be a tiny percentage of the radius of what you see. Considering that, and considering how difficult it is to look at at objects outside of the solar system. Are we in a position where we can start analyzing the atmospheres of objects outside of the solar system, or is that still beyond the reach of telescopes?
No. So my colleagues who are experts on exoplanets have been incredibly clever over the past decades at developing, really amazing techniques. So there are some gas giants, Jovian worlds, that are far enough from their star that we can actually obtain a direct spectra. And of course, a spectra in astronomy is something where we're getting at the composition of the material, and you can detect things like compounds like water and carbon dioxide or CO in the atmospheres of these bodies. Terrestrial worlds are harder to do. They're much smaller, they're closer to the star, and so you use sort of indirect techniques where when the planet is, if you have a favorable alignment such that the planet is passing in front of and behind the star along the line of sight, you could take a spectrum of the star when the planet is behind it, and then take a spectrum when the planet is to the side of the star. So then you have, spectrum of star and spectrum of star plus planet, and then you subtract out the spectrum of the star, and you're left with the planet. And another way of doing it is when the planet is directly in front of the star, it is shining through that very thin atmosphere, and you might be able to detect atmospheric components that way. And people have done this, and they have successfully done this, mostly for Jovian worlds, but now they're getting to be able to do it for Neptune-sized worlds and bodies that are larger than the size of the Earth. And the James Webb Space Telescope, when it gets up there, this is going to be a big thing that it's going to do. It's going to try to push to get it down to our ability to be able to look at the atmospheric composition of Earth-sized planets. And they're going to try. We'll see. What is certainly the case is that they're building large ground-based telescopes, 30 meters, 40 meter size telescopes. And those telescopes will also be able to approach and look at the atmospheric composition of terrestrial worlds.
So will these new telescopes and projects have direct impact on your research and your day-to-day research activities, or are they more for other people in astronomy but not you specifically?
Right. So my direct research, I will likely not be doing direct exoplanet observations. That's not entirely true. I'm on some programs where we're trying to look for young exoplanets, and I'd be super excited to be involved if people thought my input was useful. But much of that work will be done by my colleagues who are experts on the exoplanets themselves. And I'll be working on the side of modeling and trying to build Earth-like worlds and see if we can make more predictive models of their composition. That's what we've been building towards. I'm mostly looking on the formation side, trying to follow the trail of water. Where did water first form and how did it get to the planet? And fill in the question about whether, the chemicals that life needs are going to be available when the planet is born. But, like you, I'll be sitting there hoping and dreaming as we start looking for compounds such as ozone or molecular oxygen in the atmosphere of these worlds, and if those compounds are detected along with methane, then we're going to say that we've detected life elsewhere. And this is where we are today. That is, we are on the cusp of actually really being able to look for life on other planets in a direct manner. And, that's insanely exciting.
So the expectation is that we would see manifestations of life or potential of life on other planets by looking at their atmospheric compositions and if there are things like methane, is that necessarily a marker that life exists there?
Sure. So I mean, you take the data point we have, which of course is us.
Is right.
and us, right? So molecular oxygen, it was created in the atmosphere by life, via photosynthesis. Ozone is a daughter product of that, and so ozone tells you that O2 is in the atmosphere, so they're saying the same thing. Methane is on the Earth, is also created by life. And the key point is that molecular oxygen and methane should not be in the atmosphere together. That is a chemistry that is not in equilibrium. Okay? Most planetary atmospheres, the chemistry is in equilibrium. If you take the Jovian world, except for the upper parts where they're exposed to photons, or if there are some sort of vigorous motions, winds or things like that. But on Earth, the chemistry of the atmosphere is in disequilibrium because life is making this stuff. It's not going to be there if life wasn't there. The methane would just go away.
And on the topic of life, we've heard a lot fairly recently about the discovery of amino acids on comets and around, I think, even 6 months or a year ago, we heard about the discovery of phosphine in the atmospheres of Venus.
Yeah.
Do you think that has any? Is the presence of basic amino acids particularly deep, or do you think that's less of a good indicator for life than the presence in disequilibrium of things like methane?
Right. So the amino acids are the precursors to proteins. So proteins are chains of amino acids. So that's why we care about them. Meteorites have long been known to host amino acids, some fraction of which are actually used by life on Earth. And so that means that rocks falling from the sky, if they survive that passage, which some of them do, have inside them some materials that life could have used, perhaps, to jumpstart the chemistry of life. What's not clear is whether it needed that jumpstart. Okay, the planet likely could have done it on its own as long as you provided it the carbon, nitrogen, oxygen, and phosphorus, and the right environment, whatever that was. And so what's neat about that is it says, okay, so the abiotic chemistry out there in space, in this case in the bellies of a planetesimal, is capable of creating molecules that are useful for the chemistry of life. So that's pretty cool. Now the phosphine thing's a different story. So that's a detection of phosphine, or a claimed detection of phosphine in the atmosphere of Venus, and phosphine, of course, is a key component of some of the molecules of life, the deoxyribose nucleic acid, RNA, adenine triphosphate, the battery of life, essentially. And so if that's there, then that also is not expected to be there, but it's really hard to say that life could persist in such a really difficult environment as such as Venus. And there are other works that suggest that detection may be in doubt. The jury is still out. I know the individuals who wrote the paper are still working and trying to show that they're right. But in general, that part I'm not convinced about at present.
And when astronomers look for life signatures elsewhere in the universe, in these other solar systems, are they interested in just these simple elements such as oxygen or methane when they're looking for life that may be simple microbial life that exists on these planets? Or because it seems like the astronomy or the science community is very hesitant when people start talking about aliens or advanced life. But I have heard discussion of when we look at exoplanets, maybe we should be looking for pollutants like chlorofluorocarbons or CFCs, or signatures where there may be some type of advanced civilization on that planet.
Sure. So by number and by mass, the Earth is dominated by bacteria, right? So and for most of the history of the Earth, intelligent life, which I don't know how we define it, but my favorite definition is for basically SETI. When you start to communicate, it means you have electrical engineers. So we'll define intelligent life as when you have electrical engineers. Kudos to all you electrical engineers out there, so that we could build our radio telescopes and our radio receivers and transmitters and start trying to talk to everyone. Look, if life is out there, it's most likely going to be bacteria, and you have to hope that it would have harnessed the power of their sun and the availability of water to make O2. And so O2 has got to be the first thing you look for. If you want to try to look for these weaker things that might be due to life, it's hard enough to detect the strong features in the atmosphere today than it will be to detect the weaker features by some of these other things. Now, maybe I'm wrong. Maybe there's something out there that some clever person will come up with, or some wiggle of some spectrum that people can then take off on. But what is clear is the strongest lines will be things like O2, ozone, methane, water, and that's where the main focus will be. Mm-hmm. And whether you can pull out weaker features, we'll see.
Okay.
Would you characterize your research primarily as studying how planets form, or sort of the emergence of, or looking for, and or how life emerges out of the basic chemistry of space?
Right. Yeah. No. That. Yeah. I'm not. I refuse to call myself an astrobiologist. I'm an astrochemist. All right, so I study the chemistry of materials in space and how water formed, for example, or how you make those amino acids that are in those meteorites. And so I really want to know, do I supply the stuff to the planet? Is it there? And then can my colleagues who are working in the chemistry of life community, could they then use that to try and understand how life originates? I started out studying the origin of stars, and then migrated to trying to do the origins of planets, and now I'm sort of almost becoming a planetary scientist. But I will definitely not say I know anything about biology or biochemistry.
When it comes to sort of the heavier elements that we see in our solar system, so for example, like the iron in the Earth's core, and anything that's sort of heavy looking in the solar system, is that necessarily indicative of the fact that there had been a star sort of in the nearby area in the past that collapsed into a supernovae to make those heavy elements? Or can those heavy elements just make themselves without necessarily stars being their factory?
You're right. The heavy elements are made in the bellies of stars by nuclear fusion up to iron, and then above iron they're made by the explosion themselves, or perhaps in the accretion of material onto neutron stars, or where neutron stars merge. And so that's pretty clear. So the stuff we're made of came in the bellies of stars outside of the hydrogen. And of course, the hydrogen that's in our body is with H2O, right? It's with an oxygen. Helium, hydrogen and helium came with the Big Bang, lithium, beryllium, deuterium, and then most other elements. The majority of elements are made in the bellies of stars, seeded to space. And there's a gigantic galactic ecosystem where some of that material gets incorporated into planets, and then eventually the star destroys the planets and sends them back out into space, and so on and so forth.
Okay. And I guess one thing we kind of neglected talking about when we introduced the idea of planets forming is like exactly what protoplanetary disks are and like how they even come about. Because you mentioned like you work with data from ALMA, and you can see these beautiful pictures of these disks and kind of these dust lanes where early planets were forming. But how do you go from a cloud of dust in the universe to a system like our own solar system? And how do you go from pebbles to planets the size of our Earth, or even the size of Jupiter? It just seems, are there like gravitational instabilities that it just happens to collapse to form things like this?
That's an awful lot of stuff there. So the interstellar medium is dynamic, and what do I mean by that? That is exploding stars provide energy to the medium and push stuff around. And so most of the mass of gas in the interstellar space is hydrogen, and then you have oxygen and carbon present there as well, along with these tiny little particles that astronomers call dust, that are mostly silicate and or carbonaceous in origin, and they owe their origin to their birth in evolved stars, that is, stars that are on their way to dying. They make those dust grains and seed them out into space. There are complications there, but let's just leave it there. Okay, so then this dynamic interstitium has flows of material that converge and collide, and that collision leads to a shock that heats the gas up, and when it cools down, it gets denser. And when it gets dense enough that a hydrogen atom can find one of those small grains and sit on it long enough to find another hydrogen atom and make H2, molecular hydrogen. Once you make molecular hydrogen, carbon monoxide then follows, and a host of other molecules, including water. So you make what is called a molecular cloud. And parts of that molecular cloud collapse or condense to make centrally concentrated objects that have densities that exceed the average interstellar medium by many orders of magnitude, about 4 or 5 orders of magnitude. And they get centrally concentrated enough until they collapse. They're rotating, and as they collapse, that rotation leads to the formation of a central star and a disk of material. That disk of material is comprised of solids, those refractories that I talked about, and the gas. And the solids like to sink to the midplane of the disk and grow. And that's just sinking via gravity, essentially. They grow a little bit, and they get a little bit heavier, and they sink. And they grow a little bit more, and they sink. And so you gradually grow solids in the disk until you get to a dust-rich midplane, and this surrounding gaseous disk, and the planets are born in that disk of material. And we have these gorgeous pictures from ALMA where the Atacama Large Millimeter Array in Chile, so ALMA is an instrument that was built by the United States, Europe, Japan, Chile, an international collaboration. Canada was part of it, amongst others. And a $1 billion instrument where you have over 60 radio telescopes operating in concert so that you can take these images of molecules emitting photons. So molecules in these clouds or the disk, they rotate, and when they bang into each other, they gain a little energy, and that energy gets released as a photon of light, and that photon light is at a specific frequency of light. So we can tune ALMA to observe the emission line of carbon monoxide or formaldehyde or all kinds of other molecules. And so we can take images and see structure, or see evidence for areas where there's gaps in these disks, where it looks like there might be a hidden planet that has carved out that material or pushed material away. And so we might be on the verge of actually studying planet formation in action. And so we can do chemical assays and do all kinds of really amazing stuff.
And then do you always expect planets to form around the star, or can you have a situation where maybe there's a large enough dust clump or molecular cloud clump next to the forming star to have another star form? Because we know that there are more binary stars than single stars.
Sure. So the collapse itself often has asymmetries to it, so the collapse of the star, and so you could readily, about more than half of the stars are born in binaries. And in fact, we're seeing in a paper we just submitted that this binarity is kind of really neat and may affect the evolution of the system. And so you can observe, binaries, and you can see disks around two binaries. Each star has its own little disk, and there's a circumbinary disk. And so astronomy is, as always, is complicated, but at the same time, it has just innate beauty because of all the wonders to be discovered.
And I think that's a nice sort of segue into perhaps the end. As a last question that we always think is interesting, what are your biggest hopes for the future of your field? Are you awaiting hopefully exciting results? Do you think that there's anything that the field will really grow into, or do you have hopes and aspirations? I'm sure you do have hopes and aspirations for your field.
I guess one other question we neglected to ask is there life elsewhere in the universe? Because if there's anyone to ask, I feel like it would be you.
So the answer is, statistically speaking, every star that is born likely has more than one planet around it. And I suspect the chemicals of life are provided to most planets. Now, maybe some get too much, some get too little. I don't know the answer to that. But there's, billions of stars out there, billions of planets. So it's highly likely that we're not alone in the universe. The question is, how widespread is it? And, my favorite is the Fermi Paradox, which, is the classic one. If this is true, then it's life should be present everywhere. We're 4.6 billion years old. The galaxy's even older than that. So there should be billion-year-old civilizations out there, many billion-year-old civilizations who should have mastered spaceflight and come here and kicked our butts a long time ago. And they haven't. So where are they? And so that may mean that, the most simplest explanation of space travel is impossible. And we're stuck on this rock, or maybe not this rock. We can maybe go to Mars someday in the future. I don't know the answer to that, but I'm pretty convinced that life is out there elsewhere, just as a general thing. What I'm looking forward to is in the next 20 years, we're actually going to start testing that, right? We're going to start testing to see whether there's life on other planets. I won't be doing that work. My other colleagues in my field will be doing it, but it's super exciting and amazing stuff.
Yeah, it really is. That's very exciting.
Yeah, well, awesome. Thank you for taking the time to meet with us today. We really appreciate it.
My pleasure.
Thank you.
All right, well done.
Hey everyone, thank you for listening to this podcast episode. This is Michael.
This is Sam.
This is Tommy.
And this is Joe.
If you're listening to this on YouTube, make sure to like, subscribe, and share with your friends. And if you're listening on Apple Podcasts or Spotify, make sure to leave a review. All of the show notes can be found either in the description below or on our website. Thank you again for listening, and we'll see you next week with more Everything Astronomy.